Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. With less than 3 weeks to go, time is running out to register for the event we are all looking forward to, TWIMLcon AI Platforms. At TWIMLcon, you'll hear from industry luminaries like Andrew Ng, Uber's Fran Bell, and Cruise's Hussein Mahana on what leading organizations are doing to increase the efficiency of developing machine learning and deep learning models and getting them into production. You'll learn about the practices and platforms being put into place by companies like Airbnb, Capital One, Comcast, Levi's, SurveyMonkey, Zappos, and many more. And you'll get to engage with fellow data science, machine learning, platform engineering, and MLOps practitioners and leaders to learn, share, and connect on how to accelerate, automate, and scale machine learning and AI in the real world. We are super excited that we'll get to see you all on October 1st and 2nd in San Francisco. For more details, visit twimlcon.com, and while you're there, send me a message on the chat for information about our team discounts. And now, on to the show. All right, everyone, I am on the line with Gary Marcus. Gary is the CEO and founder at Robust.AI. He was also the CEO and founder of the machine learning startup Geometric Intelligence, which was acquired by Uber in 2016. Gary's the author of 5 books, including his latest, Rebooting AI, which will be available on the day this podcast is published. Gary, welcome to This Week in Machine Learning and AI.
Thanks for having me.
I'm really excited to jump in and chat with you about this book. I had a chance to dig into it. Awesome book. Let's just jump in. Before we really dive into talking about the book, I'd love to explore a little bit about your background. You spent quite a bit of your career at NYU as a professor of psychology and neuroscience. Tell us a little bit about your background and the perspective that this creates for you.
So I'm trained primarily as a cognitive scientist. My research for many years and my PhD with Steve Pinker was all about how children learn language and how children start to understand the world. So I'm a developmental cognitive scientist by training. And at the same time, I've been interested in AI since I was about 8 years old when I first learned about programming computers. And in the last 7 years or so, I've focused almost exclusively on answering the question, what can cognitive science bring to AI? So AI is currently dominated by certain statistical approaches that, from my perspective as a cognitive scientist, as someone who studies how humans work, seem a little weird to me. So I don't think of children as giant data machines, but the way that AI is kind of rolling right now, it's all about big data. And I've been trying to see what I can contribute to AI from the perspective of cognitive science.
So when you created Geometric Intelligence, was that a company that really commercialized a cognitive science-based approach, or was there a statistical approach involved in your work there?
Well, Geometric Intelligence, which was my first company, was inspired in some ways by cognitive science. It wasn't slavish to it. So there's always this tension of, if you're building airplanes, you don't want them to fly exactly like birds, because that wouldn't make any sense, and who wants to flap their wings so many times a minute? But you also want to understand something about the dynamics of flight. And in my last company, and also in this company, we're trying to take some lessons from biology, in particular from how humans think, and apply those to AI problems. So we're not, in the last company was not like trying to be neuroscientifically perfectly accurate. We're not trying to be faithful to the brain. We're trying to take inspiration from the brain. The last company, the broad problem that it was trying to address is, how do you learn from small amounts of data? And that question itself, in some ways, comes from cognitive science. I think machine learning is catching up to it now in the last couple of years, but it's always been clear from cognitive science, especially from the field of language acquisition, that learning from small data is the name of the game. Children can generalize from tiny amounts of examples. My dissertation was about how children learn the ADD rule for forming the past tense, which they sometimes use incorrectly. They'll say goed or wented or things like that. They learn that from a small amount of data. Sometimes they make mistakes and over apply it, but they don't have gigabytes of data the way that say the GPT system does now.
Mm-hmm.
And so the last company was really focused on one particular way of solving this small data problem. And our, I think, most impressive results where we were beating deep learning in terms of data efficiency. So we could learn things with half as much data without having specific priors about the nature of the things we were learning. So we would take MNIST, which is a benchmark probably a lot of your audience knows, recognizing characters. We could do MNIST with half as much data without having to build in anything about the nature of letters or anything like that. So we were working towards a general way of doing supervised learning and maybe some other things using less data. And we were inspired there by humans. We weren't necessarily doing it exactly the way that humans do, but I think the core intellectual property is something that Zubin Garamani and I developed, and I sort of set a direction that was based on some things that made sense to me from a cognitive science perspective. And Zubin, who's a brilliant mathematician, figured out how to apply it.
And so, I think a lot of our listeners, when they hear the idea of creating AI on limited data, we'll think about things like, one-shot learning, zero-shot learning. But it sounds like your approach was very different from these, or was it?
I mean, there's some interrelations, and I can't say too much because Uber owns the IP and there's NDAs and all of that
Okay.
kind of stuff. But I would say that zero-shot learning and one-shot learning, first of all, are names of problems. They're not names of techniques, and people use different kinds of techniques to do them. And they're often, I think, narrowly construed. So there are lots of problems in the world where you have some data. It's not that you have zero data, but you just don't have that much. Something I often like to talk about is what my daughter did when she climbed through a chair. So we were sitting in a Whole Foods about a year and a half ago. She was about 4.5 years old or 4 years old at the time. And we sat in a chair that had a back and then a gap between the back and the base of the chair, if you can kind of visualize that. And she had never seen the TV program, The Dukes of Hazzard, where they climb through the windows. So she didn't have any data from like a model of people doing wacky things, sticking their bodies through, an aperture inside of a chair. So this was not a big data problem, or at least there wasn't a lot of directly relevant big data. She had data about how her body worked, the size of her body, and she probably explored other apertures before. She did what a lot of people might call abstractly unsupervised learning, but she didn't use any of the techniques that we would call unsupervised learning. So it was unsupervised in the sense that she didn't have training examples saying this is the right, torque to apply to your torso in order to spin through the chair, right? The way like a reinforcement learning robot might try it a million times and get reinforcement. I got stuck this way. I didn't get stuck that way, and so forth. She just did it in the space of like a minute. And then the second time that she did it, I asked her to reenact it. And I took pictures the second time. I wish I had taken pictures the first time or taken video the second. But anyway, you look at this sequence of pictures that I took, and she actually got stuck at one point. And then she figured out how to get unstuck. And so there was problem-solving process there. And there was also kind of leveraging modest amounts of data. She had no direct data on this problem except what she got from trying it herself in that moment. And then she had a bunch of background data from other kinds of problems that she had solved. And she knew enough, maybe not consciously, but unconsciously, about physics and how her body moved and so forth that she could integrate all of that. So that doesn't fall into the paradigm of zero-shot learning, although you could sort of call it a zero-shot problem. But it's not like the things that people do in the literature, and it doesn't fall into the one-shot learning. And it doesn't really fit with how people think about unsupervised learning, where they like take clusters of things or predict the next frames in the video. It's not really like any of those problems. And yet it's kind of what little kids like my children do all the time. They say, here's some challenge that I have never confronted before. I'm going to figure it out. And that's like 80%, I feel like, I'm probably exaggerating, but it's a large fraction of what my kids do is they set new challenges. So right now, My son's a little older. He's 6.5. My daughter's 5 now. And they like play games all day long, and they don't play existing games. They play games that they invent. And so they're like, well, let's pretend that you can't fly anymore because you broke your wing or whatever. They're constantly making up assumptions and then doing problem solving relative to those reference points. And that's just completely far away from what people are doing in AI now. And part of the reason that Ernie Davis and I wrote this book, Rebooting AI, is to like reorient the field. And reboot is like start over. So we're doing great on all this supervised learning stuff where we have a ton of data, a ton of labeled data. But the reality is that's not really what the real world is like, and it's certainly not like what children do as they come to understand the world. And there's a gap right now between, I think, memorizing or doing something that's a little bit better than memorization and understanding. So deep learning is like a better way of doing memorization. You can interpolate between examples you've seen before, but it's not really about comprehension. It's not really about like building a model of chairs and apertures and bodies and understanding how those interrelate. Mm-hmm. And so what Ernie and I are trying to do is to get the field to look in a different direction that's more about comprehension and understanding and so forth. Going back to your question for a second, I mean, did my last company do all of that? No. I mean, we were a small startup. We were when we were bought, we were 15 people. We had one very specific way of solving a supervised learning problem with less data. There's a lot that goes into the human approach to less data. Another thing that goes into it that we didn't work on in the last company at all is innateness. So Chomsky's arguments, which I think are correct, is that we start with something that constrains how we learn language. We're not open to any possible language. We're born knowing certain things about language. I differ from him a little bit about what those things are. I would say we're probably born knowing that you can concatenate symbols in order to express things.
Is knowing even the right word, or is it something,
I was about to say it might not be conscious, but I'll tell you about an experiment that I did, which is probably my best known result in the psychology literature. One of the two best anyway. I had taught 7-month-old kids an artificial language, and I didn't tell them the rules for the language. I just gave them examples, 2 minutes, and that was enough for 7-month-old babies to figure out the abstract grammar. So they heard sentences like la ta ta, ga na na. So they had an ABB pattern. Of course, we're psychologists, we counterbalance. So others saw the AAB pattern, and some saw an ABA pattern, etc. So you hear one of these grammars, and now you have to hear new sentences that are made up of either, they're all made up of the same words, but some of them new words. And some of them also have a new grammar, some have the same grammar. So you hear ABA sentences, now you get tested on ABB sentences or not. And what we found was that the 7-month-olds, they're not paid for their participation and they're getting course credit for intro psych. They're just sitting there listening, but they want to know what's going on here. So they hear 2 minutes of this stuff and they can already tell when you change to a new grammar. They start paying attention more. So they habituate, they get bored by hearing the same thing over and over again, and then they dishabituate, they show interest when we change the grammar.
I was hoping that this was going to be teaching them Klingon or Dothraki, although it was probably maybe a little bit after that time.
My favorite line of all of the Star Trek movies was about hearing Shakespeare in the original Klingon. The subjects in our experiment heard something that was even Proto Klingon, proto-human. In any case, they pick this up. And then what happens in developmental psychology is if you do an experiment, you show that kids of a certain age can do things, then if it's interesting enough, people try to extend it in different ways, as many people have done for this. And they also try to show that even younger kids can do it. So somebody's actually shown using brain measures, it's not a perfect experiment, but a pretty good one, showed that even newborns are doing the same kind of grammatical analysis that our 7-month-olds were doing. And we showed that kids were more likely to do this with speech than with like musical tones and stuff like that. And if they could get the gist of it from speech, then they could transfer it to musical tones, but they didn't analyze musical tones in the same way. It's a very interesting set of results, but the bottom line for what we're talking about is it does actually suggest that some of the roots of grammar are there as early as we can test children. As an aside, something can be innate and not be there at birth. So, my capacity to grow a beard was innate. I didn't learn how to do it, but it wasn't expressed until I was, I don't know, 14 or 15 years old. People in developmental psychology literature get confused and think if it's not there at birth, it's not innate. But the human brain comes out of the oven before it's fully developed. Not everything that happens afterwards is about learning. In any case, I would say that we have innately that. We also have innately probably a distinction about like subjects and predicates, like these entities are undergoing this change or something like that, and various other things. And so when we start getting exposed to language, we have some hooks already built in that we can attach that to. Now you compare that to the kind of reinforcement learning for language acquisition experiments that DeepMind has played around with over the last few years.
And just if I can jump in here, I think to contextualize, reinforcement learning is one of the things that many in the field are really excited about because in a lot of ways it appears as, one of the closest things we have to learning the way children learn, right? There's an environment, there's an agent that interacts with that environment and learns things, if we can put that learning around air quotes.
It's all true, but it's missing something. And that's sort of where I was going. So yeah. I think you characterized correctly what reinforcement and deep reinforcement learning is to do. And at the level of abstraction that you described, it has to be right. Right. I mean, what you do is you try things in the environment and you look for feedback. And one of the forms of feedback is sort of, am I right or am I wrong? And that's what does this lead to a good outcome or a bad outcome? And that's what reinforcement learning is all about. And, nobody sane would argue that some of that happens.
Right. And there's a lot of conversation around and how difficult it is in practice, for a variety of reasons, sample inefficiencies, and how difficult it is to get the reward function correctly. But I think you're saying something more fundamental about the difference between real learning and reinforcement learning.
Yeah, in improv school, they teach you yes and.
Right.
Right. So yes and. So the and here is, and you need a whole lot of other stuff to make it actually work. So the problem right now is like the stereotypical version of this is the Atari game system that DeepMind built, which led to their sale or was part of why Google bought them for all that money. And what was cool about it was they could play a lot of different games. They could play Breakout, could play Space Invaders, and some of them they could play at superhuman level. And there was nothing built in about the rules of any of those games, which, by the way, is not true of their Go demonstrations and so forth. But that original demo, it was really like interesting intellectual proof of concept. However, it didn't really work that well in the sense that if you change the circumstances at all, it all fell apart. So Vicarious had a really nice demo, and actually my company had a similar demo, my last company that we never published, but makes the same point. What Vicarious did was they took Breakout and they moved the paddle up a few pixels. And you have like this famous video on the web of the DeepMind thing playing Breakout, learning to break through the wall, and people kind of talk in very cognitive language about how the system has learned to go through the wall and whatever. And then when Vicarious moved the paddle up 3 pixels, suddenly performance went from superhuman to mediocre because the system hadn't really learned what a ball is, what a paddle is, or what a wall is. What it had really learned was the statistical contingencies that worked on the screen in which it had been trained. And that's much more superficial than the human way of playing Breakout, which is to learn about the kind of physics within the game of the ball, the paddle, and the bricks. And so going back to reinforcement learning, DeepMind's right to set it up as a reinforcement learning problem, but they're actually wrong to build nothing at all in. And when they want to, because then you just, if you start from zero, you just don't get that far. So in fact, when they play Go, which is in some ways a hard problem, in some ways not, they build in the rules of Go. They build in Monte Carlo tree search, which sets up the problem as kind of if I go there, then you go there. They don't learn that stuff. And they've been putting out all of this kind of PR around a very blank slate approach, and where there's nothing built in, but they don't actually do that when they solve the hard problems. And they had this paper that really kind of aggravated me called Mastering Go Without Human Knowledge. And in fact, they had like a world-class Go player on the team, and there's lots of ways in which human knowledge was embedded. I have an archive article, ARXIV, maybe you can link in show notes, taking apart all the human knowledge that actually went in there. But they're doing it kind of through the back door, like hey, nobody pay attention to the fact that we built in the rules and carefully designed how many layers through a lot of experimentation and haven't tested it on a different size board. What we really need to do is to think about the principled information that needs to be built in conjunction with reinforcement learning so it will work. You could say that what my daughter did was like online reinforcement learning, but she wasn't just like, what happens if I do this small torque on this limb? She was trying to figure out how to do this relative to a pretty rich model of her own body and
Right.
of the three-dimensional geometry of the world and a knowledge about the physics of like rigid objects. She probably would have done it differently if the back was made of string and she knew she had more space and it was flexible. She could
I
do a
think
lot
you
of
said
counterfactual reasoning in the context of reinforcement learning.
yeah, yeah. I think you said an important word there in model. One of the recurring themes on this show that I've talked about quite a bit that really just kind of jumped out for me after a number of interviews was like this pendulum swing from a world in which the way we understood the environment that we interact with is through creating these models around physics and engineering, et cetera. And now we've kind of gone to the other end of the pendulum swing, and there's a lot of focus and excitement around statistical approaches. And there is a lot of interesting work happening kind of at really more of an equilibrium point where folks are looking at marrying the model-based approaches and statistical approaches. And it sounds like what you're really proposing is something similar to the, in support of AGI, artificial general intelligence, or GAI, general artificial intelligence, whichever of those acronyms you prefer. Do you agree with that?
I would slightly rephrase what you just said, but basically I agree with it. The problem right now is we're mostly focusing on narrow intelligence, and deep learning is a very good tool for that, or deep reinforcement learning for certain narrow problems. But those tools are not good for general intelligence, whether you want to call that AGI or GAI or what have you. But the kind of intelligence that is inherent in a flexible person, for example, you can solve problems in different ways if the assumptions change a little bit from what you started with. And to get there, you need to do exactly what you just said. You need to marry the modeling approach, which may use, for example, symbolic techniques from classical AI, with the more statistical techniques that we have now. And if you look at humans, that's exactly what they do. We do some perceptual stuff that seems to be kind of driven by statistics and a lot of experience, and we do some, abstract reasoning and language and so forth that don't seem to use the same mechanisms. Kahneman's cut on that is system one versus system two, the kind of reflexive system versus deliberative system is the way I like to talk about those.
Thinking fast, thinking slow.
And I think that the AI techniques that we have right now are good. I wouldn't even call it at thinking, but at classifying, which is a little bit like his system one. Classifying, I've seen this pattern before. I haven't seen it, or it looks like this other thing that I've seen. But we're not right now as a community focusing that much on the kind of system two stuff where you deliberate, where you recognize your assumptions are wrong and you change. And that's where the model stuff lives. The system one stuff, like you don't have time for a model. You're just relying on kind of memory traces effectively of things you've seen before. The system two kind of stuff, you have to have a cognitive model. What is going on here? What are the causal relationships between these entities? If I change this thing, what would happen to this other thing? That kind of reasoning, which humans do all the time. I mean, they do it, in grad school, but we also just do it in daily life. That part's not being captured, and so much money is going into the deep learning side that it's kind of perverted, I think, the mission of AI, which was originally to go after general AI. It was much more, I think, originally sympathetic to learning from humans. Right now, the kind of mathematicians and cluster builders have the upper hand, like computer cluster builders have the upper hand, because these techniques are yielding a lot of short-term fruit. But I think it's perverting the overall direction of the field. And that's what this book is about, is to try to correct the ship, not to throw that stuff overboard. We need it too. The deep learning or some successor to it's going to stick around. But we need to have some focus on other things, like how do you do causal reasoning about what happens if I do this thing to this system, or temporal reasoning. Where is this system going to be 20 minutes from now? I just saw a paper showing that people are getting pretty good at using deep learning system to predict the next clock tick, like the next, say, quarter second in a video or the next frame in a video.
Mm-hmm.
and they were pretty terrible. This was just bouncing balls, billiard balls. They were pretty good at that, but they had no way of sort of predicting what would happen 5 minutes later. So like you could look and say, well, they're going to come to rest and they're going to be scattered in distribution like this. And the deep learning systems couldn't do that. They could make these very short-term predictions essentially by consulting a library of videos they've seen before, interpolating over that library. But that's not the same thing as temporal reasoning. So I know, if I tell you that I have an airplane ticket to go to California next week, you can predict that I'll be at the airport, on Tuesday morning, or if I give you enough information, you can make these long-term predictions that aren't about like looking at frames in a video library. They're about reasoning about abstract entities. Like, okay, he needs to be in California on Tuesday, then he's probably going to have to go to the airport to do that. He'll probably have to go through a security line. You make all these inferences about what's typical and what might happen. What if I missed my flight? And then what would be the alternatives I would consider? You can do all of this higher level reasoning that's very different from predicting the next frame of a video.
I guess one of the questions I have that's maybe a little bit of a pushback on that is it just okay that we're making a lot of progress in a narrow way in AI right now? Like even in the book, you talk about, curing or treating cancer, inventing new materials, addressing climate change. Big AI, right? AGI, could have a huge impact on those areas, but we're also having, small but significant impacts in a lot of those areas today with the narrow techniques that we have. And so,
well, there's two things there. There's two things there.
Okay, go ahead.
One is I just hate leaving that much potential for human progress on the floor. Like, I think we could be doing better. I think with the amount of money that's being invested right now, if it was spent a little bit more wisely, we could make huge progress. And I think, it's worth thinking about that rather than just sort of taking the next step because it's the obvious next step. Sometimes the obvious next step's not the efficient one. And the other, so that's one reason. Like, I'm an idealist. I'd like to see us make as rapid progress as possible. And I think we could do that by compensating where the ship is going a little bit. The other side of it is we're relying a lot on these techniques right now that are pretty dumb. And the people who made them are smart, but the techniques are dumb in the sense that they don't have cognitive models of what's going on. They're just relying on brute force or variations on brute force. So by using those techniques that don't have rich understanding of the world, we get in trouble. So people are applying those techniques, for example, to driverless cars. But then the driverless cars, like a couple days ago from when we're recording this, it looks like a Tesla drove into a tow truck that was parked on the side of the road.
You mentioned this example in the book a couple of times about fire trucks and tow trucks. I had not heard this. This is a thing?
I had mentioned the tow truck actually when we finished the book. Books go to press. They take a while to publish. In the book, we mentioned fire trucks and police trucks who were stopped on the side of the road. And then a few days ago in Moscow, a Tesla rose into a tow truck. So, there's clearly a pattern there. Mm-hmm. And it's continuing pattern even as we're recording the interview. You want a system where at least if you have a couple of fatalities, and there's tractor trailers too that they've run over. So we've had multiple fatalities from the two fatalities from running into tractor trailers, and I don't think any of these were fatal. But now multiple accidents, basically running into emergency vehicles stopped. Well, we want to have an AI system where you can specify in abstract language, don't run into stopped emergency vehicles, and have the system that's smart enough to figure that out. Mm-hmm. But what we actually have are systems that need a lot of labeled data, and there aren't a lot of labeled data of tow trucks stopped on the side of the road, and nobody thought to get them. Maybe they'll collect them now, but there'll be some other case. This is what I mean by edge cases or outliers cases. There's going to be some other kind of emergency vehicle that looks a little bit different, and a person's going to be able to reason that must be an emergency vehicle, but it's not going to be in the data set. And so the other part of the answer to your question is we're using this techniques now. Lives are at stake. So we have to do something. Either we outlaw, driverless cars until we figure out something better, or we work actively right now to think about what a better approach to AI would be.
Yeah, I thought this was a really well-stated and important point in the book, and that is around this core issue of trust. Other words around what you were just describing, and that we, particularly, in the general public sense of the word, we don't understand the way the things we're calling AI today are operating, and don't understand the failure modes, and we, as a result of that, we trust them too much, and there's a potential, as you were just describing, that we put them into situations where lives are at stake and people don't understand that they're likely to fail in some ways.
That's right. And the same thing's happening over and over again. So like people put a lot of stock in face recognition and it's really not that good. So you have like a lot of police departments running around using it and it effectively adds to our profiling problems and it's not that good. All these things, they might be like 90% accurate but we're using some of them in situations where we need more. So it's fine if an advertisement recommendation system is 90% accurate. But if we use a face recognition system in crimes and it's 90% accurate, that's actually pretty bad. You don't want 1 in 10 missed calls there. And a driverless car thing, even if it's 99% accurate, that's not nearly good enough. And so when we're doing mission critical things with AI that we don't understand, that's the interpretability problem you were just referring to, and they themselves don't really understand the world in which they're operating, that's a recipe for problems. And that's why the whole book is really about trust, is because we are increasingly assigning autonomy to systems that don't really understand the world and that we don't really understand, we are getting ourselves in a bad position. The worst case here is AI could get shut down. We could have a winter kind of from without. There've been multiple AI winters because funding gets dried up. Like if enough people died on one day in a driverless car thing, like Congress could say, enough, no more AI research.
Mm-hmm.
And we certainly don't want that. And so we have to make people's expectations realistic. You and I haven't talked about hype today, but that's another theme in the book. And we have to branch out and look more broadly in the space of possible architectures, including a bunch of things that are really out of fashion, like symbol manipulating classical AI. Not that we should be rebuilding that stuff. We should be borrowing from it. We should be borrowing from the old stuff, something old, something new, the right kind of marriage, as you were saying before. But we need to do that if we're going to be counting on the machines. And we are. And we can't put them all in a box. So we got to do better.
I'd like to come back to the areas that you see as having promise in taking us past where we are today. But before we do that, you mentioned hype, and I think that is going to, addressing the hype and kind of counterbalancing it is going to be, a big contribution of this book. A big part of the first several chapters of the book is really trying to address that hype. Like there are a lot of really good examples in here, where the hype underlives or where the hype doesn't live up to, or where the reality rather doesn't live up to the hype. And, in particular, you spend a lot of time talking about reading. Walk us through, that as an example and, some of the ways that, you gave some examples about Microsoft and Alibaba and the Squad results that, were published some years ago.
Sure.
There are a bunch of examples in there.
Sure. So I don't have the book in front of me, but basically the case that we made there is there were a bunch of, in that specific example, was a bunch of media accounts saying that Microsoft had just achieved superhuman reading or had matched human reading, excuse me. And the reality, and there were even news stories that said humans are running out of jobs and the sky is falling kind of stuff because of this result.
Mm-hmm.
And what had actually happened was Microsoft did slightly better than it had done, it or anyone else had done a couple weeks earlier. And they now happen to match humans on this one test, which was called Squad. But Squad is not really that much of a test of reading. It's really a test of can you underline a piece of a passage that corresponds to a question? And that's easy sometimes, but a lot of times, that's adequate sometimes. But most of the time when we're reading, we're trying to figure out things that aren't in the text. We're trying to go beyond the text. So if I just want to, read a story about what Donald Trump did today and say, who's the president, you can probably match the words president and Donald Trump with a system like that. And you can call that reading if you want. But a lot of reading is about reading between the lines and you make inferences. So I can say somebody walked into a store and you can figure out they're probably a human being. And, all kinds of things that are just logically obvious or inductively obvious to human beings all of the time that go into the process of reading. And that test just didn't happen to measure any of them. And you would never hire that machine to summarize news stories for you, or to tell you, especially like the implications, even the most obvious implications that aren't written on the page. And reading isn't focused throughout the book. One of the reasons that Ernie Davis and I wrote this book is we had written op-eds and things like that trying to make some of these points, but there's a real mismatch between what current machines do and what you actually need to do in reading in terms of all the inferences that you draw. So we had some worked examples a little bit later in the book, not in the opening chapter, where we look at a children's story and just show all the things that you figure out when you're reading something by the woman who wrote Little House on the Prairie. Just like a paragraph and all the inferences. And no system around even tries to do that. And we wanted to go at length, in depth, to try to help people better understand why the direction, the thrust of current AI research is just nothing like what you need to actually read. Just wrapping up on hype for a second, one of my favorite parts of the book is just early in the first chapter, we give advice about questions that people at home can use when they read news stories. News stories are often like the byproduct of some press release that a big company puts out. And there are some very good people in the media, but there are a lot that just kind of report the press release. And so the press releases often wind up more or less unedited in media. So we give a set of questions that you can ask, like, did they do this on some toy problem or a bigger problem? What were the data like? To help people to be able to go and read the news and have a healthy sense of skepticism. And this should be true for all of science. Of course, anytime you read science, and probably anything that you read in the news, you need to be careful. So we try to arm people with a set of questions to sift through the hype and figure out, like, is this the real result? Does this mean systems can read, or just that they passed this one test? What else do they need to do?
Right.
And for that matter, was any skeptic like me, for example, consulted to give any kind of counter view? If not, that's a sign in itself that this is press by press release.
Yeah, I've got this particular one dog-eared in a note in my notes where I call it Gary's bullshit detector. But since I do have it in front of me, the 6 points were stripping away the rhetoric. So what did the system actually do? And so trying to get to, is it actually reading or the squad results? How general are those results? Is there a demo? A lot of times we see these results either in academic papers or, commercial, and there's not a demo that anyone can go see. If there's a comparison about the system's performance relative to humans, then, which humans in particular are we talking about and how much better? How far does succeeding in this particular task actually take us towards building genuine AI? And then the robustness of the system, which I kind of took as like failure modes, like where does it fall down? Is that what you meant there?
You will notice that the direct consequence of writing this book is that I founded a company called Robust.AI. One of the things that I exaggerate a little bit for comic effect, but it's also true. Ernie Davis and I wrote this chapter on reading that I was just alluding to. And then we wrote a similar chapter on robots, like talking about the gap between a demonstration of a robot doing a backflip and having a robot actually work in your home, like Rosie the robot. And the gap is just immense. And the biggest problem is robustness. You can make a lab demonstration of any one action, but you really want the robots to decide for themselves what to do. I've started thinking about a kind of distinction between automation and autonomy. So the field of robotics has learned very well how to automate certain things if the environment doesn't change at all. But they're not very robust. So, you can pack 1 million iPhones into boxes, and as long as the boxes are exactly where you expect them to, it all works out. But if something unusual happens, then the system may have no idea what to do about it. And that's basically what the problem is with the driverless cars. Those are robots. And they're fine under ordinary circumstances, and then it rains, or someone has a hand-lettered sign, or there's a stop tow truck that isn't in your training set, and they don't work very well anymore. And so the key challenge, I think, in robotics, which is a great test of how good your AI is to be robust, to get the same thing to work when the lighting is different, when there's somebody there that you weren't expecting, when there's an object that you weren't expecting, when your map turns out to be out of date or wrong, all of these kinds of things. Robustness is really a measure indirectly of intelligence. An intelligent system will recognize that its assumptions were wrong and compensate for that fact. A blind system just keeps doing what it's doing. So I'm driving on the road. I don't see anything in my little test set. Seems good. And I just drive right into the tow truck. Like that's the opposite of robustness.
One of the chapters in the book is called Insights from the Human Mind. And it jumped out at me that you said mind and not brain. And I was curious, what was that distinction for you and what?
Sorry, that was very deliberate. My view is that neuroscience is a prestige field right now, but hasn't come up with the goods. And psychology is the study of the mind, and more generally, cognitive science is the study of mind, and actually already has a lot to offer that isn't really being paid attention to. So someday we will build better AI by understanding the wiring diagram of the human brain and getting some insights from it. But right now, we don't understand that wiring diagram. We don't understand even basic things like how does the brain do short-term memory? So if I say, let's pause, I'll call you back in 5 minutes, you'll be expecting my call in 5 minutes. You don't need 1,000 trials to, hammer that into your brain. But we don't know how the brain does that. We really don't. Like, ask all the neuroscientists how did we do that? I'll call you back in 5 minutes. How does that work? What are the brain? People can sort of say, well, something lights up in your prefrontal cortex, and like it's so hopelessly vague. So neuroscience is not going to be our salvation in the short term. On the other hand, we know a lot about, for example, the dynamics of human memory from a cognitive science perspective. And we know a lot about things like goals and plans and intentions and beliefs and desires, stuff like that. We don't know how they work in the brain, but we obviously have them. And we can build those things into our machines. And so the point of that chapter is to look at cognitive science and see what clues it gives us. So I've already alluded to a couple of those, like it's okay to have innate structure. The machine learning world right now is so obsessed with learning, it doesn't want to build anything in except for convolution. Well, convolution is actually an innate prior. Your technical people will know exactly how it works, that allows you to recognize an object that's in different places in a visual field. In cognitive science, they've called that translation invariance for a very long time. And that's a clever way of building in, convolution is a clever way of building that into a neural network. We need much more of that. But there's this like attitude in machine learning that's cheating. You shouldn't build anything in. There's a crazy attitude. Look at biology. It spent 1 billion years building in the right set of genes to make us have brains that could react with the environment in a flexible way. Like, let's not throw all that away. So that's one example of the things that are in the cognitive science chapter.
Yeah, one of my recent guests said, and in fact, I think this became the title of the interview episode, and he was talking about something very different. I want to make that clear, but that, AI is a systems engineering problem. And it sounds like in a lot of ways you might agree with that,
I do.
But a lot of the pieces of the system that we need to engineer don't exist yet.
I agree with that too, although I would say that we are, as a community, not doing a great job of leveraging the ones that do exist. That as a community, we're fragmented. So there's a small kind of classical AI group that's kind of doing what it's always been doing and not really paying that much attention to deep learning. There's a huge deep learning community that's not paying much attention at all to classical AI. They're kind of smug. They're like, we have good equations. We don't need that stuff. And so the divisiveness between the cultures, which goes back all the way to the 50s, has kept people from doing the right systems engineering. But I also agree that we probably need to invent a whole bunch of new stuff too. So, we can do much better even with the existing tools. And I think if we worked harder to integrate the existing tools, we'll get a clearer idea of where we actually need the new tools. And that's, part of the thinking behind my new company with Rodney Brooks, the Robust.AI company.
And is this Rodney Brooks of Mythical Man Month fame?
This is Rodney Brooks' best known, I guess, for the Roomba, which he co-invented.
Okay.
And a fantastic set of blogs about kind of what's possible and not that he's been writing recently. He was the chair of MIT's AI CSAIL laboratory for many years. He's done many great things. And it's fantastic that we have him in the company.
From a kind of concrete technical perspective, what are the opportunities? And it sounds like, maybe a context for this is, the things that you think that we have that we could be integrating into these systems.
So, I don't want to say too much in a way to protect details of what I'm thinking about within the company context, but broadly speaking, deep learning is part of the picture, clearly. We need to do perceptual classification. But we also need the kind of knowledge representation that classical AI used in order to figure out how to represent common sense in machine interpretable form. There has to be a way of putting together the vast knowledge that humans have already accumulated with the kind of experiential knowledge that deep reinforcement learning is good at acquiring. Like that has to be the focus.
Mm-hmm. And you mentioned a couple of areas in the conversation thus far, causal reasoning, temporal reasoning. Like, are there any, independent of what you're doing with the company, are there, things that folks that are practitioners that are, listening to this and wondering, okay, how can I buy into this idea of, kind of swinging the pendulum back to the middle and doing more kind of model-based approaches. You mentioned knowledge representation. Like, what's there for folks? Where should folks be looking to really start working in this direction?
I would say they should do a couple of things first, which are to read the new book of mine, Rebooting AI with Ernie Davis, because we talk about what common sense is and what are the challenges in representing it and so forth. And I think we do that in a more accessible form that is in the technical literature. I think people should look at that. I also think they should look at Judea Pearl's very recent book, The Book of Why, on the question of causal reasoning.
Okay.
So I think those are the two best places to start. They're not the most technical places. Both books refer to lots of technical literature from there. Another thing I would say is everybody in the field should know about the CYC psych system that Doug Lenat created, which still exists, been working on it for 30 years. Most people think it's a failure, and I think everybody who wants to work in general AI should have a view about that system, what it can do, why it didn't entirely work. What strikes me a lot is a lot of young people in machine learning have never even heard of it. And it's the most sophisticated and comprehensive attempt to have a machine understand everyday reasoning, like how objects work, how people interact with each other, kind of intuitive physics, intuitive economics, intuitive psychology. And maybe it didn't work, but I think that the mountain that Doug Lenat was trying to get across is one that we still have to get across. I don't see how you get a reading system, for example, that really works if you can't ask part of the system, like, what happens when somebody loses their wallet? You want to know that, like, they care, that their money is in it. They might try to go find it. And you're not going to get all of that by just memorizing, movies that you watch, which is kind of what I think the field is trying to do. So Lenat had an approach, and I think people need to use that as a mental crucible. So, when you're getting started, you should read, Rebooting AI, you should read The Book of Why, and you should read something about psych. You can find various review papers that Lenat has written over the years. And you got to start there by understanding what the problem is. None of the three things that I just mentioned have the answers. They just have a better cut on the questions. Ernie and I don't know exactly how to build a general purpose AI, but I think that we are able to articulate some of the problems that need to be solved that are being neglected.
Fantastic. Well, Gary, thank you so much for taking the time to share with us what you're working on.
Thanks very much for having me. It was a really fun interview.
All right, everyone, that's our show for today. For more information on Gary or any of our other guests, visit TWIMLAI.com. Register now for TWIMLCon AI platforms. You definitely don't want to miss out. As always, thanks so much for listening, and catch you next time.